Welcome to EGME-333 Fluid Mechanics. In this video, we're going to discuss major loss and minor loss inside a pipe system. So let's begin by considering the pressure drop for a steady, incompressible turbulent flow inside a horizontal round pipe of diameter capital D, which can be written in functional form as the change in pressure delta P is a function of the following variables: the mean velocity capital V, the pipe diameter capital D, the length of the pipe L, the surface roughness epsilon, the dynamic viscosity mu, and the fluid density rho. From the Buckingham pi theorem, we can identify that there exists 7 different variables within this problem, and this corresponds to 3 different reference dimensions. They include the mass, the length, and time. So consequently, there exists 4 dimensionless pi terms. By solving for those dimensionless pi terms, we can rewrite the dimensionless functional form of this problem as delta P over rho V squared is equal to a function of 3 different dimensionless variables, where one of them includes the Reynolds number, the first term, the length of the pipe over the pipe diameter, and the last term is what we refer to as the relative surface roughness, which is the ratio of the surface roughness times the pipe diameter. We can further simplify this expression by recalling that in a fully developed pipe flow, we often observe that the pressure drop is proportional to the length of a pipe. So we can factor out the L over D quantity from the function V to emphasize that the pressure drop is proportional to the length of the pipe, where a larger value for L, the length of the pipe, will correspond to a larger pressure drop, delta P. If we define the friction factor lowercase f to equal the pressure drop delta P times the pipe diameter capital D, this quantity divided by 1/2 rho V squared, the dynamic pressure, times the length of the pipe, then we can state that the major head loss in a pipe flow is given in terms of the friction factor, where the major head loss H sub L is equal to the friction factor F times the ratio between the length of the pipe divided by the pipe diameter times the mean velocity squared divided by 2 times the gravitational acceleration g, such that the friction factor F, a dimensionless quantity, is simply a function of the Reynolds number of the flow and the relative surface roughness, where the relative surface roughness is given to us by the ratio of the surface roughness epsilon divided by the pipe diameter capital D. Determining the value of F depends on whether we are dealing with a laminar flow or a turbulent flow. In the case of a laminar flow, the friction factor F is given to us by the number 64 divided by the Reynolds number of the flow, Re, where we define the Reynolds number for a pipe flow as equal to the product of the fluid density rho times the mean velocity capital V times the pipe diameter capital D. This quantity is divided by the fluid dynamic viscosity mu. If we are dealing with a turbulent flow, we also have to consider the relative surface roughness of the pipe. The value of F can be obtained from experimental results, which are plotted in the famous Moody plot, or you can utilize the Colebrook formula. The other category of head loss are minor losses, which are pressure losses associated with all other components of a pipe system that are not straight sections of pipe. Typically, to compute or estimate the minor loss of a pipe component, we have to know the value of the minor loss coefficient, capital K sub L, where the minor loss can be computed as H sub M is equal to the minor loss coefficient, capital K sub L, times the mean velocity squared, v squared, divided by 2g. Note that the value of the minor loss coefficient k sub L is strongly dependent on the geometry of the component considered, and may also depend on fluid properties. But often, the minor loss coefficient is defined by the specific component or geometry of the component that you are working with and the corresponding value of the Reynolds number. And these values tend to depend on empirical data.